Awesome. Well, welcome back. I'm happy to be back, actually. Had a good trip, but I'm like being in front of students again. So today is one of my most fun lectures on measuring and analyzing performance, because that's what we do a lot. And some of that you do in industry as well, but it depends where in industry, obviously. But you do it particularly when you're in research. So for those who may end up in the trustworthy systems group, this is highly relevant. For those who end up in industry, it's still relevant. So going through what is performance evaluation, why you want it, that's pretty brief. That's sort of boilerplate stuff or motherhood stuff. And then benchmarking, this is where it gets interesting. What do you need to watch out for when you're benchmarking? How do you do it properly and how not to? Profiling to help you understand, and then do performance analysis, for which profiling is an important tool. And then, okay, once you have established performance and got dug down, how do you actually understand what it is? So, what's performance? That may sound like a trivial question. It's obviously how a system will actually deliver some service and at what cost in the end. But it goes way deeper than that, because there's different ways to establish performance. And one question is there an absolute measure of performance? Sometimes there is, sometimes not. If you have to do relative performance measurements, which is what we mostly have to do, then is there a good baseline for that? And so, what are we comparing? Sometimes you're interested in best case performance, sometimes in average case performance. Question is, what does that mean? Best case is relatively well defined, average is much less. Expected case, so this really, given a expected workload, what's the performance going to be like? This is ideally what you have. And then sometimes you're interested in the worst case. Of course, you cannot properly measure the worst case. You can only really measure a bad case. To establish an actual worst case, you have to do some theoretical analysis. Okay, so it really need to, before you start measuring, this is the questions you need to ask yourself, right? What am I really after? And in particular, depending on what you're after, it matters whether you have a hot cache or a cold cache performance analysis, right? Hot cache is what we're mostly interested in, because that maps typically to certainly best case and often hopefully average case. Whereas if you're after bad case and in sort of data centers, that's becoming a really big issue, tail latencies, right? If Google runs a query, they're not only interested in having the average query time being really fast, but they're particularly interested in how's the tail latency. And the tail latency can be order of magnitude or two higher than the average case. And then, okay, this is what the user experience, right? If there's a bad tail latency, and they're worried about that. So there's no yes, no, or simple answers to any of these. They all depends on the context of why you want to establish performance. So you need to really understand what you're trying to achieve here. Having said that, we get to how do you measure this, and that's of course benchmarking. And I'm not typically the person who puts comics in their slides, but this is an exception. I couldn't resist that one. I actually paid for that one. I've seen that in real world life, believe me. Okay, and there's an old saying, there's lies, damn lies, and benchmarks, and that's absolutely true. A lot of benchmarking is worse than damn lies. People cheat a lot with benchmarking, and this comes down to when you see some performance measurements, you need to understand what's the benchmark that's being run and what are the assumptions to really make sense of that, because otherwise you can show anything. I can produce almost any performance if I hide exactly how I do it, right? If I choose my input data, my configuration, then you can almost always show almost everything. So some of the considerations here are you using micro and macro benchmarks, and I'll go into that, what that means. use benchmarking suites, how can you make sure that your results are complete, that they're significant, that you're comparing against the right baseline, etc. And a lot of there is benchmarking ethics. As I say, people cheat, and that's not good. So let's have a look at some of these. In general, when you benchmark for research or development, some reason for benchmarking is you want to buy a system, right? You're somewhere some manager in industry and you want to establish, okay, where do I get the best bang for the buck? And I run benchmarks. So this is then a good case where you just need to establish what is the performance and compare different systems on the same workload. And hopefully you choose a workload that's representative for what you want to do. If you're in development or in research, and almost all of you will more likely be in development or research than in management, at least for the next 10 years or so, then you typically change something to the system. You either build something new or you improve something, and then you want to run benchmarks to establish performance. And what's really important and what is often ignored is there's two aspects there. When you do something that's supposed to improve the system in some way, in particular when you try to improve performance, then obviously you want to show, well, it actually helps performance. So this is a progressive criteria. You need to demonstrate that you actually progressed. But at the same time, there's the conservative criteria, meaning that for everything else that I didn't particularly want to optimize with this change, I need to make sure that performance doesn't really suffer. And often there's a trade-off, right? You improve something. The SCL4 IPC implementation is a good case, right? You have the critical operations are fast pass, meaning there's some really tight code that gets there as quickly as possible. And I'll talk about that in detail when we talk about microkernel design and implementation. But you do some extra tests, which strictly speaking penalizes the other parts of the systems that aren't fast pass. And of course, if it's just a couple jumps or so, then that shouldn't be significant, and you can easily say, okay, that doesn't really matter. But that may not be always so obvious. So that means if you really want to demonstrate that you've done something good in the sense of increased performance of some critical workload, then at least you need to make sure that you don't overly penalize other workloads that are also relevant. So that's the conservative thing. Really, both are important. And I get to read a lot of papers where people just do the progressive thing without the conservative thing. And sometimes, like reading what they did, I'm fairly confident that it does have a negative performance impact on other operations, and they don't look at that. So without having actually measured it, I have to make a worst case assumption. And that's also a form of cheating in a way. And then this is really important. If you do this kind of really analytical kind of benchmarking where you want to establish that you actually did improve performance, or your performance is not as good and you want to try to understand what's going on and how you can help it, then it's really important that you have a model of the system. In most cases, that's not an explicitly defined model. It's somewhere in your head, but you need to have a model. You need to have an idea of how you expect the system to react to what you're doing, right? Without such a model, you're completely in the dark. And it's really important that you are conscious what your model is, and I show some examples of that. So your model is obviously a simplification of the system. That's what models inherently are. And it implies a hypothesis, right? You've done some fast pathing of some critical code, for example, and you have this hypothesis that this should help the performance where I'm interested in and should not damage the performance where I'm not. And that needs to be supported by your model, and then in the end you need to test it. And it's really important that when you do this kind of analysis that you explicitly confirm or reject your hypothesis. And you can only do that if you're really conscious of what it is. So this is what people often ignore. They just run off blindly, and then they get results which in the end they don't understand. So you think before you measure, you think about what do I expect to happen, if I vary these parameters, what do I expect the effect is? And then you measure and show that either system conforms to your model, that means yes, you know what you're doing, or it does not, and then you really have to dig deeper. And this is again where ethics come in, where you really have to objective and fair, etc. And I'm getting to sort of baselines and all that later. In terms of how you progress practically, there's the general distinction between micro and macro benchmarks. Now, there's no clear-cut line here, but basically a macro benchmark is something that represents a realistic workload. Now, inherently, when you're trying to benchmark something, you have to sort of simplify your system to distill it into some sort of a representative workload, right? And this is where things can go wrong, and it's really important that you have your model, etc., that tells you you're on the right track. But it's basically something that's supposed to represent a realistic scenario of application. So in that sense, it tends to be a relatively complex. You run some big process, a web server, or something like that, some complete kind of system. The opposite is the micro benchmark, which basically tries to probe a particular operation. And micro benchmarks are not really suitable for establishing overall performance, but they're an analysis tool. They're sort of a way of drilling in. So, for example, you run a web server. The web server is slower than you expect, so you have a model of the performance, and it doesn't comply with the model. Well, okay, so you hypothesize maybe it's the system call that's too slow. Then you try to measure that system call in isolation. That's a micro benchmark. And obviously, that again implies that you have a model of how that particular thing you measure with your micro benchmark has an effect on the overall performance. You're not done once you've done the micro benchmarking and maybe optimize that particular system call, because then you have to go back and show that your macro benchmark now actually behaves as you expect it to. So this gets us to my first benchmarking crime. I have this list of benchmarking crimes which I collected over the years, and they are now known in the community. People cite them in call for papers for conferences, for example. And it's sort of a list that's grown over the past 14 years, I think. One of them is using micro benchmarking only. I didn't invent that. That's well established in the community, but it's still something that people often do wrong. The other thing is standard versus ad hoc benchmark. There's for typical system scenarios, there's a bunch of standard benchmarks. For example, the SPEC, the System Performance Evaluation Committee or whatever. It's a non-profit organization that started off building benchmarks for measuring CPU performance. Now they have all sorts of things. They have Java virtual machine performance. They have web server performance, etc. Really broad spectrum of benchmarks. And the advantage of these is they sort of geared to give you a reasonable overall performance picture of some kind of system, whether it's the CPU itself or your whole web server or whatever. And they're suites in the sense they consist of a bunch of individual benchmarks. And the idea is people spend a lot of thoughts in coming up with these suites and really balancing them, trying to explore a whole range of application load scenarios in order to come up with a simple overall measure. That doesn't necessarily mean it's always the best thing, but it's a really good thing to have. So, and then there's Embassy benchmarks for embedded systems, the Yahoo cloud server benchmarks, etc. So different kind of suites for different application scenarios. If you have a suite that's useful for what you're after, then by all means use it, definitely use it. Again, if I read a paper and they're not using a standard benchmark suite when there is one, I'm starting to ask questions, difficult ones. Sometimes you don't have a choice of an existing benchmark suite, standard benchmark suite, because for what you're after there isn't one, or your system is an AOS system that's very immature and limited in functionality and you can't run a web server on it, etc. then you have to go to ad hoc benchmarks. And that always means you basically don't have really, you don't have a good comparison base because no one else is using those. So these are some general things to keep in mind. As I said, this is mostly motherhood and apple pie, but this is sort of the background I needed to present. Any questions up to this point before we sort of dig into more interesting details? No? Okay. So, technical question. If you have a suite that consists of multiple independent benchmarks, which all are run, how do you derive an overall figure of merit for that benchmark suite? So let's assume we have a very simple suite that consists of two benchmarks, 1 and 2, and we try to compare 3 different systems. And if we run on them, this is the performance patterns we get. Assume these are seconds, for example, right? They're times. How do you derive a reasonable overall figure of merit for each system so you can compare them? The goal, of course, is I want to know which system is faster for my purpose, so which one should I buy? And that is a single decision that needs a single metric as it for the decision maker, right? So how do I derive from these different timings here a single metric?
I forget what they're called, but I've seen people use tables where they assign each metric an importance, essentially, and then the metric is scaled by that importance for the particular.
Yep, that's what they do. That's what they do anyway. Yes, but you still have two different benchmarks, and you need to derive a single number from that. And yes, you may have to weight them, and the weighting may depend on your particular application scenario. But what's the process you use to combine these two numbers for each system into a single number?
I mean, naively, you would use the arithmetic.
Naively use the arithmetic mean. Yes, that's what I would do for sure, and I bet most of you would. So if we do that, then we end up with this number. So what's better? If these are seconds, then it looks like it's a dead heat between system X and system Z, and system Y is bad, right? Is that the true answer? If these numbers have absolute meaning, then it actually is. However, that's in most cases not the case. Like if you do weather forecasting, then the time to run this thing has absolute meaning, right? You want to be able to finish it in time to get a meaningful weather forecast out. So there's meaning to absolute times. In most cases, benchmarks don't have absolute meaning, the benchmark results, right? They're just relative numbers that say, okay, on the suite 1, on benchmark 1, system Y is the fastest, system Z is the slowest. But benchmark 2 behaves differently, and I need an overall figure of merit. So let's do a test. Let's say we normalize the performance to system X. So we take system X as 1 and express everything else in multiples of the system X performance, right? That's pretty standard. And then we average those. And we get, okay, system X is the fastest, so we should buy that one. Is that the right decision? How can we find out?
Normalize to all systems.
Again?
Like normalize to all systems.
You normalize to the next one. Yes, that's normalized to system 2, system Y. And of course, it comes out as 1 because we normalize it. And it turns out it's the fastest. Okay, something is wrong here, right? This is not a good way to come up with an overall metric. Any other suggestions? How can we do better?
Normalize all of them and take the one that does best.
And then average over the normalization. That would be one way to do it. I'm not convinced that this is a stable way, like something that gives you good results always. The answer is, and someone could have guessed it, I don't expect that you really know that, is to use the geometric mean instead of the arithmetic mean. And then it turns out, if we normalize the system Y, they all have the same performance. If we normalize the system X again, they all have the same performance. So the conclusion of that is, in this case, the assumption here is the absolute numbers don't matter. It's only relative performance on each benchmark. And the benchmarks have equal weight, in which case it doesn't matter which system you buy. In average, in average is a dangerous word to use here, but overall they perform the same. There's assumptions here, right? It's the absolute numbers are meaningless and the weight is the same. Obviously, you can adjust for different weights, and a geometric mean will allow you to do that. But the general takeaway is usually the geometric mean is the thing to use because it's invariant under normalization. And that's definitely a good property. So the rule here, arithmetic mean for raw numbers that have meaning in themselves, I should have added here. If anything is normalized, which they normally are, then use the geometric mean. Okay? Questions here? No, then let's carry on. So one of the benchmark suites get abused as well. People find all sorts of ways to lie. And this one is something I really read a lot in papers. And if I do, then I am pretty much on the reject button. We evaluate the performance using spec CPU 2000, and the figure shows typical results. What does that tell you?
They ran it a bunch of times and cherry-picked it. They ran it a bunch of times and cherry-picked it.
Yeah? Typical results meaning like they show spec CPU 2000 has 20 or 30 individual benchmarks, right? They show you 5 or 10. What's likely happening?
Was it typical to what? Typical to the average case?
Well, this is obviously sort of a hand-wavy statement that tells me almost certainly they are cherry picking. In matter of fact, just sort of in some cases, just looking at what those benchmarks do, I mean, you basically know their behavior. You can actually often tell that they definitely are cherry picking. And of course, that's a highly unethical thing to do, to cherry pick the best results and pretend they are representative. That's a really bad benchmarking crime. So using a subset of a suite without really good justification is a benchmarking crime. Sometimes you have to. And again, this is not untypical in OS research, where you don't have the full functionality to run the whole thing, right? In which case, yes, you have to knock out some which you cannot run, in which case you really need to be open about this and be totally upfront and basically accept that, well, your result may not really be that representative. Okay. Yeah.
Where was this paper from? Like, which paper? Was it on operating system?
Probably one that never got published.
Like what field was it? Like related to operating systems? Or
Yeah. Basically, I read operating systems papers. But I mean, this is not a unique incident. I've seen that a lot. Much less so. I think my benchmarking crimes list actually did have an impact. I see fewer papers that I review that have clear benchmarking crimes in there. So hopefully things have improved a bit, but you do see them. Okay, so sort of related to partial suites is partial data. And this is something that can be just as bad, but it's often not quite as obvious. So take this scenario, which I actually also see a lot. You see, okay, people measure, say, network performance, whether they do driver work or evaluate how the system in total deals with networking, etc. Maybe they added a security feature and want to argue that, yeah, it costs performance a little bit, but it's only a little bit, right? And so you see this, well, our more secure networking system has 10% performance degradation. And they justify that by saying the throughput drops by 10%. Now, if you have a network system and the throughput drops by 10%, what could the cause be for this reduction in throughput? Say you just change the networking stack, right? The drivers, the client, the NIC is all unchanged, but you did some change to the networking stack and you lose 10% performance.
Oh, could be a lot of things. Could have dropped packets somewhere, buffer flows.
Why would you drop packets somewhere?
Well, I guess if you've got a queue that's full.
Yeah, because the system can't keep up with the load, right? So this is a case when you're CPU limited. And if you're CPU limited, then losing 10% in throughput is actually, it's fair to say then this is a 10% degradation because the CPU is already at the ceiling. You do some changes, you chew up a bit more CPU time, and that expresses itself by losing packets, okay? Because you couldn't, presumably you lost packets already before and now you lose a few more. An alternative scenario is when you're not CPU limited, you could be latency limited and you just add more processing latency and that reduces throughput. And that could have completely different underlying issues, because then you might see something like that. And this is, again, this is a simplified made-up case, but I've seen things like that in real life. That you have 10 megabit or 100 megabit per second throughput initially, and that drops to 90 megabit per second throughput, so you lose 10% in throughput. But if you look at the CPU, the first case, the CPU is maxed out before and after, right? So you're CPU limited. And then you process, with the amount of CPU you have, you process a few fewer packets, and that is sort of a measure of the performance. That's a reasonable thing. In the other case, your CPU usage jumps massively, right? Before that, you could keep up with that load with 20% of CPU, and now you suddenly use twice as much CPU and can't keep up with the load. Something is really bad there, and chances are your latency limit in this case. Now, I think we would agree that in the second case, calling that a 10% performance degradation or overhead is very misleading, because you double your CPU load, right? So, what's the right way to compare these things? The throughput changes as well as the CPU load changes at the same time. How can you end up with a single figure of merit? That's typically what you want, right?
Well, we have to consider how much we care about CPU and how much we care about CPU usage and how much we care about.
Well, okay, there's cases where you have basically the rest of this. It doesn't matter how much CPU you use as long as it's less than 100%. These cases are becoming pretty rare these days because increasingly our devices are energy limited. And it doesn't matter whether it's a big data center, they pay huge power bills, and they care about how much energy they use. Or you may have a little embedded IoT device that's ambiently powered by solar cells or using parasitic radio waves, etc. And there you care about energy use as well. So 20 years ago, you could say energy use doesn't matter, and therefore the CPU is basically paid off, and it doesn't matter how much load I have on it, and that is free, that you could get away with that argument. These days, it's usually wrong. So you can't say, I don't care about CPU time in most cases. So the thing is, you really need to look at, if you want to get the performance or the overheads, you need to get how much time does it, how many cycles do I use to process a packet or a kilobyte of data. That's the real metric, right? That tells you really the performance of your system. So if you use this proper figure of merit, cost per unit of data, then you see a huge difference between the two systems where the one goes up, the cost goes up 10%, whereas in the other case, the cost goes up more than double. So calling that 10% overhead is definitely a damn lie. And so this is another really bad benchmarking crimes to just assume that throughput degradation represents overhead. It may, but it may not. And without looking at the CPU load, I cannot tell. Now, many network systems are CPU limited. As long as you know that's the case, then that's all fine. But you need to state it. Okay, questions? So now we've sort of got an overview of do's and don'ts of benchmarking. Now you have your performance and it's not what you expect it to do. You want to improve it. So how do you do that? You need to dig into the system. And profiling is one really important hammer you have at your disposal for doing this. So profiling means that you collect not just the overall execution time, but more fine-grained data of the system. For example, how much time is spent in the kernel versus the user land, how much time is spent in the driver versus the network stack, sort of more fine-grained, right? Ideally down to single procedures or even single lines. And that's what profiling is about. And the problem with profiling is, unless you have hardware debugger, so if you have JTAG interface and the hardware to make use of that, that basically gives you an ability to profile your system without interference. But as soon as you use software means, which in many cases you have to, then your profiling inherently interferes with the system performance because the profiling takes time, right? You want to count how many times you're in the kernel or how much time you spend in the kernel. You need to run code that actually measures that. And this competes with the execution of the system. It competes for CPU time, it competes for cache space, etc. So again, unless you have the sort of this offline kind of profiling using hardware debuggers or cycle accurate simulators, any profiling interferes with the performance, and that's something you need to be aware of. And basically, a core observation there is you need to combine your profiling with benchmarking to show that, well, if I run the benchmarking with profile enabled and disabled, the performance doesn't really change much. That's a good result, and you know you can really take your profile data probably is meaningful. If there's a big change, then you have to really care for. You need to understand that you're actually impacting the performance of the system, and I have some examples of that. So in the end, profiling allows you to really see where it's worth drilling down for your performance issue. Basically identify the performance bottlenecks. And there's nice tools for that if you can use them. So whoever used gprof? Only one person used gprof, okay. They don't teach you that in first year, they should. And because that's an extremely, very easy to use and very powerful tool. Unfortunately, you can't use it on W04 because the infrastructure isn't there, right? It's a microkernel. gprof itself relies on system services. But it's a really nice tool. It basically combines tracing with statistical analysis. In the end, the way it works is it interrupts the execution at somewhat randomized times, and then just looks at what's the program counter and collects the program counter values in the buckets, and then it does some post-processing which relates that back to the source code, and then you can see where the time is spent. So this is a typical gprof output where you can see, well, in this example, in this run here, a third of the CPU time went on the open system call, and 1/6 into a mem copy, etc. And there's really these 5 things that contribute. The dominating one is the open system call, and then there's the other 4 functions. If you see something what do you learn from that? What does it tell you?
You're making too many open syscalls.
Yeah, okay. It tells you, well, the hotspot is the open syscall. Whether that is any use for me is a different story, right? If I'm just tuning application performance, then okay, maybe I can reduce the number of opens. Unlikely, actually. So I basically have to accept that one and then focus on the rest. However, if you're trying to optimize the operating system, that may be very useful information. You know that open syscall is a bottleneck. And that's actually sort of an extreme case, if you like, because open is clearly expensive, but normally amortized by the actual I/O you do. So this must be just opening very short files a lot. Yeah?
You could also look at like how much time you're spending per call and see if that's something you can optimize.
Yes. And it gives you the number of calls as well. So in this case, you see, well, the reason is you call open a lot. It's the most called function of the ones that matter. So maybe that's something you can look at, right? So this is not the full picture, but it really gives you a starting point where to look at. And then you can drill down further. In particular, you can sort of have a more fine-grained analysis. It tells you who calls these things, for example. And by establishing the call chain, you may have to learn where it makes sense to try to put your effort. That's really what this profiling does. It tells you where to put your effort in trying to optimize the system. So this is what we had until maybe 20 years ago. It's basically statistical profiling. These days we had much more powerful things. Like what? Who has actually profiled some real code ever? Only one person used gprof, so probably not too many. Hey? Performance counters, yes. They are the system developer's best friend, trust me. They are awesome. And these days, all the CPUs have them, and they're really, really helpful for analyzing performance. So the performance monitoring unit has things called events and counters. So events are things you can count, for example, cache misses, cycles the CPU is stalled, complete number of cycles executed, complete number of instructions executed, etc. These are events. And these are things you can count, and then typically the CPU supports a lot of them. These days they can be hundreds, but you have only a small number of actual counters, and a counter is what you can actually use to collect events. So the number of counters tends to be relatively small, sort of typically 4-ish. That means if the system, this PMU offers you 4 counters, that means you can count 4 events concurrently. And if you need more, then you need to what's the term? Time multiplex it, right? But you can actually get a long way with just looking at 4 counters. In most cases, that's enough to understand what's going on. Sometimes you just have to try harder. And they typically can be configured in 2 ways, either just counting, and then you can read them at intervals and find out how many of these events happened since the last time I checked, or they can count down and trigger an interrupt when they reach 0. So you can say, interrupt me when we're after 10,000 cache misses, for example. And both are useful. And some architectures give you user-level access to those. In most cases, it's really restricted to the OS. But the OS then can export an interface that allows you to use them at user level. And this is what you get when you run oprof in Linux. I think there's now something newer than oprof, but it doesn't matter. It's sort of the same principle. It basically is a user-level interface to these performance counters, and it allows you to profile both the kernel and the user land. So this is an example of what oprof gives you. It's again sort of a whole bunch of split by functions in this case, and it tells you what performance counter. So this is oprof configured to use the CPU clock unhalted, which is basically the cycles actually executed. Well, cycles while the CPU was not stalled. And the rest is stall cycles that are due to various events. And it tells you then how many of these happened during the sampling period and who consumed it, what the percentage of the overall is. So in this case, this is obviously running a full system, not just a single application, and it tells you, okay, the C++ compiler is really the dominating thing here. Whether that's a surprise or not is a different question. What else do you see here?
Win.
Yeah. It's a long time since I ran this. But
Well, are those system processors like KDE init, VM Linux, are those system stuff?
they would be system daemons, yeah. What sort of things is remarkable there? If you look at down the list here, what sort of should strike your eyes? You see the profile itself, right? And this comes back to what I said earlier. Profiling inevitably interferes with system execution, right? And you see here the profiler chews up a few percent of CPU time. In most cases, that's benign, right? A few percent, okay, I get some, there's some variance in the results anyway, and a few percent typically don't matter. So this is a good result, and you can really home in on the stuff that's otherwise there. But this is actually, it does show you that you have to have an eye on this, yep?
Is this a standard way of measuring how much overhead the profiler adds? Are there other ways to measure how much your profile is interfering with the program? Or is this like the standard way to do it?
Well, this may not actually be precise because you get effects that you don't see. One thing is, in order to do this statistical sampling, or it's not statistical sampling using the performance counters, you need to program the performance counter, you need to access them, etc. Particularly if it's driven by interrupts, then this is probably not accounted in this O-profile daemon. So it's not the full story. But chances are, if you see it so far down, then the other effects are even smaller. But there's no clear answer, right? You don't really know how much impact you have. The only thing you can do is bound it by comparing a run with a profiler on and a run without profiler. And if their execution time is within 2-3%, you know you get fairly safe, unless you dig too far down. Did you have a question?
I was going to say, I would have thought that the CPU usage of the profiler would only really matter if the program you profile with the CPU limited.
Sure. Well, not really. I mean, for the same argument I made before about why CPU usage almost always matter, because you pay for it one way. In the old days, cycles were essentially free because the energy use was almost not affected by the number of cycles you consume. Well, in some sense, that's actually more true than before, but in others not. So it's a complicated story. But generally, cycles are generally not free. So there's examples of that. And then you can actually drill down, right? You can again look at who calls that, what's the breakdown of this program into different units. VM Linux, that's the kernel. And so you see how much of that is user level versus kernel time, etc. So, as I said, OPROF is a user level interface in Linux to the PMU. And if you do SEL4, you can't use OPROF. You have much more. You basically have to do most of the things yourself. I've got a thesis student trying to build a more OPROF-like profiling infrastructure for SEL4, but at the moment we don't have it. But general takeaway is the PMU is awesome. It's a developer's best friend, and it can tell you a lot about the system. This is the PMU events that are supported by an old ARM v6 processor. So this is, I don't know, 15 years old or so. These days, I didn't bother updating it because it becomes too complex. You have literally hundreds, and most of them you don't particularly care about. But here there's some really useful ones, right? I cache misses, D cache misses. This is very often, particularly if you're in the microkernel world, the level 1 cache performance is often critical to understand what's going on. Instruction buffer stall. This is an instruction fetch that's stalled because for some reason the data is not available, or the instruction. Decache write back stall. So this is, remember the caching lecture when I said that when you need to load a new line into the cache, you need to free one first. So this is the cost of writing a dirty line back to memory, so you get a free line to load data in there. PC changed by software. What the hell is that? Any idea?
That would be a jump.
Yeah, that's how you do a jump on the ARM architecture. The ARM architecture treats the program counter as a general purpose register, and you do a jump by just writing an address in there. It's a bit unusual when you come from the Intel world, but that's so basically this counts the number of jumps. Yep.
So is that an ARM only thing, and then branch executed would be Intel thing, or like x86? Like what would be the difference between branch executed and x86?
Branches, I'm not actually sure. There may be, for example, Intel has a distinction between jump instructions and branch instructions. Branches are relative to the program counter, and maybe it's something similar to that. But I don't know offhand. But you can see branches executed versus branches mispredicted. So that's obvious. This tells you how spaghetti your code is, basically. Load store, unit store, write buffer drained. Remember, I talked about the write buffer. This is where you had to wait until it's made space again. Instructions executed, so that's the total instruction counter. And we have the cycle counter. So that's always good to compare the instructions executed versus the cycle counter. If you have a single issue processor, then ideally they are the same, but in reality they are not because there's stalls. So the difference there gives you the total number of stalls, and then you can, for example, if you measure that and cache misses, then and they are the same, then you know, okay, my stalls are pretty much all cache misses. Otherwise, no, I need to look at other possible events. Right? So really useful. And yeah, as I said, the developers' best friends. So this is the big tool we have for analyzing the performance. And in the second hour, I want to look at how that actually works. So now we have a break of 10 minutes. See you back in 10. Okay, let's go back. So having established how we measure performance, we now have to look at how we analyze it. And there's a whole range of different aspects to that. And one is sort of leads us into another benchmarking crime is the establishing the significance of results. Everyone should understand that anything you measure has measurement errors, right? It's very rare that you can measure something absolutely without measuring errors. Although in our space that does exist. But in general, you have to assume that there is some variance. And as I said, computers highly deterministic, so we do have cases where you can measure something with zero variance. But at least for the things we are after, unless it involves wide area networking, where there's obviously some really uncontrollable degree of randomness, the systems are deterministic enough that we can at least expect these measurement errors to be small. And therefore, if you watch your variance, your standard deviation, you expect it to be small. And this is a real important warning sign that if your standard deviation is not really tiny, then there's something going on which you don't understand. Which, getting back to what I said earlier about models, you have a model of your system, and certainly for if we do things like measuring things, performance of systems on whether it's Linux or SCR4, whatever, without involving wide area networking, then I assume a high degree of determinism and therefore tiny standard deviations. If not, then my model is wrong, right? There is some other effect. Could be a hidden parameter, could be something going on which shouldn't be going on, etc. In any case, that's an important point to drill down. So if you measure performance and you don't look at the standard deviations, then that's a benchmarking crime, because you may be fooling yourself and others in doing so. And typically, they should be tiny. In this case, it may just be enough to state, yes, we looked at standard deviations, they're all negligible. That's fine, I'm happy with that. As long as you look at that, because you often really miss important things. So, and this is where computer science so far is not much of a science and not even a serious engineering discipline, because you see a lot of papers where people never quote any standard deviations, or at least say that they're tiny, which they really should. And I'm fighting that battle continuously. So at the very least, besides the mean, you need to report the standard deviation or say that it's really small. And obviously, if you've ever done any physics labs or anything like that, you should know that if the results are within a standard deviation of each other, then they are insignificant, right? You can't really distinguish them. So if you have a standard deviation of 1.5, then 10.2 is not significantly different from 11.5 because it's within a standard deviation. But in general, it's just, even if it's outside a standard deviation, that's not really necessarily significant. So, for example, if something is 2 standard deviations apart, what does that mean? What's a standard deviation? What does it really represent?
It generally calculates about 68% data of the first standard deviation.
If you have a normal distribution, then the standard deviation is and this is some term I don't know in English, it's where the slope changes from negative to positive and the other way around. That's that width of the bell curve is your standard deviation. And if you have a normal distribution, then yes, 68% of the samples are expected to be within plus minus 1 standard deviation from the mean. So that's really what the standard deviation means. And that means if you had 2 standard deviations apart, what's the interval? Do you know the interval for 2 standard deviations? 95%, yes. So that means even 2 standard deviations, there's still a significant number of data outside, so you can't really be certain that this is a significant effect. And typically people go for 99%, which is close to 3 standard deviations, 2.5 or something like that. But what's the assumption here? A normal distribution. How do you get a normal distribution?
Take enough tests to be under the central theory. So about at least 10, 20 tests.
Yeah, so for something to be normally distributed, there's really 2 requirements. One is you need to have enough samples, because otherwise you don't get a clear distribution. But the other is also it's continuous variables. Normal distribution strictly applies only to continuous variables. We almost never have continuous variables, right? We have digital computers. Things are not continuous. So we get at best a binomial distribution or something like that. There's this, a theorem that says if you have enough samples, the binomial distribution converges on a normal distribution and you can treat it as a normal distribution. And the rule of thumb is about 50 samples or so. So if you have at least 50 samples, then you can, with some justification, treat your distribution as normal. However, it's not guaranteed that it is. So you really have to be careful. And so 2-3 standard deviations apart is generally not enough to say some 2 values are statistically different, significantly different. Right? Keep that in mind. So which is fine because in most cases our standard deviations are tiny anyway. There are a couple of cycles or so. So you're either the same or you're really well apart, in which case, yes, if that's the case, then you know you're fine. And the t-test is the thing that actually allows you to test that, the principled way of testing, whether it's statistically significant or not. But we don't typically need that machinery. You're either really fairly close and there's no significance, or you're many standard deviations apart, in which case, you know, there is an actual effect. So let's look at an actual case. So this is, I just ran that at one stage. Use one benchmark of the spec CPU 2000 suite, doesn't really matter what it is. And it gives you this curve. So this is the same benchmark run multiple times. So this is not iterations within the benchmark. It's just the same benchmark run multiple times behind each other. And you see the results are not constant, right? Your mental model probably says, I run the same program multiple times, I should get the same result, right? The same time, execution time. We don't. What's the effect here? There's two effects. The first one is, for whatever reason, takes longer, of the order of 10%, no, actually less than, it's a few percent if you look at the numbers, right? I'm sort of cheating with the scale here. Martin Gardner, who used to write the Metamagic or the mathematical whatever column for Scientific American many years ago, he's long dead unfortunately, he coined this term chart abuse, and this is the case of chart abuse. I make the effect look really bad when in fact it's actually tiny if you look at the numbers. So don't get fooled by that. It's a few percent. And yes, most likely that's caching, right? So it's a warm-up thing. You started, the first run had cold caches and then the repeats had warm caches. Or it could be just a load time into memory or whatever. So what we take away from that one, we typically want to warm up. Big deal. But then why are these times not constant? So these are execution times. Why are they not the same? They fluctuate. There's actually 3 distinct values we can observe. So how could that happen? Explain.
Like usually computers work on ticks, right? So like you can only time this.
Yeah, but look at the execution times. They're 40 odd seconds. But it's got to do with time. What you see here is a timer resolution. And you can actually read from this diagram what it is, because you have this very clear distinct values. You can say that you can actually read out that the difference is 50 milliseconds. So it's a 20 hertz timer. And that gives you an actual accuracy of this. It's amazing what you can read out of these graphs, right? From this graph, I could read that this system used a 20 hertz timer. So it's always good to really look at what's going on there. And it comes back to, I have a model in my mind of the system, and the model says, okay, there's some warm-up which I need to get over, but then the execution time should be totally deterministic. They're close to, but not quite. Okay, why? Well, because I have this coarseness in the measurement of time, basically. Because otherwise you would expect sort of a more smooth distribution, obviously. So this is the time. So again, comes back. Use your mental model, right? Be aware of what it is and really be alert to something diverging from what your mental model of the system predicts. This is really, I can't iterate that often enough. Yes?
Are the 2 peaks around 5 also just timer resolution?
Yeah, they're one of the 3 values, right? You get the value of 44.75, 44.8, and 44.85. Okay. So if you do have noisy data, which sometimes you do and can't prevent, well, first thing is you really think about, if you have very noisy data, try to think about how can I make it less noisy. So if you benchmark something on Linux, unless that's completely impossible for the services you need to measure what you're doing, run the system in single user mode to get rid of all the various daemons interfering, etc. Use a dedicated network when you do networking as much as possible. Obviously, if it contains really wide area network experiments, you can't do that. But if you're just doing sort of networking driver evaluations, use a dedicated network to just get rid of interference. So as much as possible. That should go without saying, right? You try to measure a system that's as clean and pure as possible. And if you can't do that, then sometimes you can do things like ignoring outliers, and there are some statistically sane ways of doing that. Sometimes, and we see that pretty frequently, and I think I have an example later on, yes I do, of a bimodal distribution where most of the data are clustered around one value, and then there's another cluster that's much smaller. And if you understand why that's the case, it may be legal to just ignore that other cluster and go for the first one. But whenever you do that, you're basically manipulating your data, and you need to be extremely careful about it. You really need to understand what you're doing, and you need to well document what you're doing and justify it. So that's really important. Otherwise, that's a really vicious benchmarking crime. It's basically throw away some data without really strong justification. Okay, so here's another, and this is just what I was getting to, another real example, this time on SCL4 and actually fairly recent. So this is a student doing fast pathing the signal system call. And what he measured is, so we are after the signal, and there's two scenarios. You either signal a thread with lower or equal priority, or you signal something with higher priority, and the implementation is quite different depending on the two cases. And so you see the performance, the minimum, they're more than a factor of 2 apart, and that's inherent. But the really curious thing here, and he compared to the cost of the null IPC, so this is the baseline of the null system call of just getting in the kernel and out, and you see the signaling to low is very close to the null system call. It's just about 12–13% more expensive. So it does very little. It just gets in the kernel, has a very efficient fast path, and gets out again. Whereas the signal to high is much more expensive. It's even more expensive than a full IPC. And that's again inherent. But what's really curious here is for the first 3 lines, we have standard deviations that are 0 or 1. And this is basically what I expect, right? Because we have this very deterministic computer, why should we have variances? So I'd expect these single-digit standard deviations. But in the signal to high, it's huge. It's basically almost the same as the minimum of the execution time is the standard deviation. So that's a huge standard deviation. Something is really wrong here. My mental model, when looking at that, does not support this case, right? I expect the standard deviation to be small. So why the hell is it big? Or better question, what can we do to find out what's going on? That's really what you want, right? You ask yourself, something is wrong here, is not lined up with my mental model, my underlying system hypothesis is wrong. How can I find out where I'm wrong? You could profile that path, and hopefully that will tell you something, yes. And so we don't have well, we did with some way or other, and it's sort of irrelevant how we got to the data. We did that, and we basically recorded, again, this is the same benchmark repeated over and over, and record the execution times. And this is what you see here is an extreme case of a bimodal distribution. Most of the values are relatively low, before 400, but and turns out it's exactly every 8th run has a way higher value, more than 3 times as long execution time. And that's why you have this huge standard deviation. So something is wrong here. Why does that happen? It's hard to say without further information, right? This is then when we start speculating. So we're tuning our model and then trying to test it out. And my theory looking at this is it's almost certainly, there's nothing in the kernel that should trigger that. So it's almost certainly an interference from our test setup with what we want to measure. So again, and this is sort of typical what you do, what you run into, that your benchmarking interferes with what you're trying to measure. And most of the time, the interference is negligible. Here it's significant. And the theory, and we pretty much convinced looking at various, using the PMU, looking at various indicators, is what we have here is a limit in the memory bandwidth of this device. Remember in the cache lecture, there's a write buffer between L1 and L2 cache, and another one between L2 cache and memory. And when there's lots of writes, the write buffer fills up, and eventually it stalls, and it stalls the CPU until it's flushed. And that's almost certainly what's going on here. And so what we can read as this is the real system call cost, because that's the one, the good value where it's not interfered with by memory stalls. Or at least I would claim this is an upper bound to the real system call cost. It's almost certainly the real system call cost, but there could be other effects happening. As long as you have any of these interference, you cannot be sure. So why would that happen? In order to understand that, we need to look at the actual code for doing this benchmarking. This is the code that's presently in SEO4 bench. So that's our standard benchmarking suite for measuring SEO4 performance. What it does is it executes a syscall in a loop, collects timestamps, and then for each iteration, it writes it into a buffer for later processing. And then once the actual benchmarking run is over, we compute the mean and the standard deviation. So what happens here is that we write a lot of data. And the fact that this interference, this funny stalls happen on the one version of the signal kernel call and not on the other, means that it's probably that the slower version of the signal system call touches more memory than the fast version, and it touches enough memory to get this interference with this write operations resulting from the benchmarking suite. There's no complete proof of that, but this is a pretty good speculation. And the counteractions actually confirm that. So assume that's the case. Our writing to this log buffer saturates the memory bandwidth of the system, and we get memory stalls. Then what can we do to avoid that? So my hypothesis is we have too much write traffic. Some come from the kernel, some from the benchmarking suite. So how can I stop the two from interfering?
Could you avoid using the buffer by computing the main standard deviation as you go along?
Yes, and this is how I would have written it in the first place, because I'm trained as a physicist and I wouldn't do it this way, but you're quite right. Before rewriting this, we did another test, because clearly you have the memory stalls that are not happening in every iteration. So a single iteration doesn't saturate the memory bandwidth, but if we have enough of them quickly enough, then we saturate it. So a simple way to test that is just introduce a delay between subsequent iterations and see does that get rid of the bimodal distribution. Indeed, it did. So, okay, that means my hypothesis is probably correct, and it's that. And then the next step was, yes, do the proper thing, and rather than filling up a lot of data, I mean, this is calling for trouble, right? SEO4 performance is very sensitive to certainly the cache footprint and stuff like that, and sort of flooding, at the very least, we're flooding the cache here by writing a lot of data. So this is really asking for trouble, and we avoid that by just doing it properly, which is we accumulate the time and we sum up the execution times and the square of the execution times, and from those two values plus the number of iterations, we can compute the mean and the standard deviation. That's standard practice. And then we can keep all the data that's required for doing the benchmarking in registers, so we know we don't interfere with the memory system, and hopefully get cleaner data. And if we do this, then we get much better results. Notice the numbers are not the same as before, because before that was on an optimized signal system call. This is the unoptimized one, but the effect is still the same. We have a huge standard deviation on the, with the left code, and a order of magnitude reduced one with the right-hand code. It's still higher than I feel comfortable with. 15 is still more than I expect. I expect literally less than single digits, so 2, 3, maximum 5. So there's still some more to understand what's going on, but it's a big improvement, and at least we know that the syscall cost we measure is actually a reasonable approximation to the real thing. And it turns out it is smaller than the minimum we got here, which tells you there's some degree of interference even in the good case. And certainly the maximum is dramatically reduced. So the fact that this maximum is still significantly higher than the minimum is sort of an explanation for this standard deviation. So probably still some minor bimodal thing, but it's much less of an issue. Questions?
In this case,
Hey?
in this case, if you redo the if you reprint out that graph that you had, now that you've done an optimization, and or supposing you could, and you find that those peaks are in the same place, would you be able to, in that case, disregard the second mode of output?
Yes, if you know it is an interference from the benchmarking rig, which you really have to justify this belief very strongly, then you can say, yes, my real system call cost is the minimum. In particular, if you see that in this case it was the two modes of the distribution each had extremely low variance, right? Basically none, and that's a good that's a justifiable case for saying, okay, it's the minimum that I'm after. Okay, so having gone through this, and again comes back, have your mental model of your system in mind, compare the data to the mental model. If there's disagreement, dig deeper, or you shoot yourself in the foot. All right, back to a bit of motherhood and apple pie. This is again sort of standard experimental techniques. You need to vary the inputs and check outputs. This is notorious that hardware sometimes optimizes stuff away, not just compiler, but even hardware. We saw that when we were doing file system measurements, where a student just wrote all null blocks to the disk, and the disk discovered, oh, they're the same as before, I just need to write it and throw it away, and you can easily fool yourself there. So a good idea is actually ship random data. In a case where the actual data that you transport should not matter, it's important to actually vary it to avoid effects like that. Access patterns matter because lots of hardware is optimized for sequential access patterns. That's principle of locality, right? We know in average that's a winner. Sometimes it can be really bad, but it means that if you have these sequential access patterns, then some hardware optimization may kick in that give you seemingly better performance than you actually have. Checking outputs are correct. So yes, if you write something to disk, make sure what you read back is actually what you wrote out there, or you may have a bug that gives you really fast I/O. And sometimes this is not feasible, in which case you need to at least do random checks. So basically do 2 runs of the benchmark, one with checking, one without, and then just do the checking to make sure that the things are actually functionally correct, and then turn it off for doing the benchmarking. Sometimes true randomness is bad. It's sort of good in terms of testing the functionality, but of course it can make things hard to reproduce. So the best way is not using real random data, but use a deterministic pseudo-random sequence. So pseudo-random number generator where you fix the seed and rerun the same experiment with the same seed. But then, of course, it's also important that you vary the seed and check that the result is essentially still the same. Another real-world example. This is quite a while back, if you can see from this platform spec. So a Dell Latitude, Dell laptop with 1.8 gigahertz Pentium M. So that's a really dated processor. But the instructiveness of the example doesn't go away. So the student was actually working on energy management, operating system level energy management, and did some benchmarks. And one of the benchmarks from the spec suite, so-called 12 benchmark, showed some really weird behavior. So again, this is multiple back-to-back executions of the same benchmark. Mental model says we should have a flat curve here. Reality is huge fluctuations, right? These are like 20%. This is not sort of the tiny 0.5% effect we've seen before. This is really huge. This is on Linux, running the same, it's a normal user level program, running it multiple times back to back. What the hell is going on? I couldn't tell, right? So what do you do? I gave you the answer before. Yeah, you use it, your PMU, that's what you've got it for. It's exactly what you got it for. So, and the student was diligent. He looked for his standard deviations, otherwise he would have never noticed, right? So he did the right thing. He found, oh, this one benchmark, I've got huge standard deviation, what the hell is going on? And so, okay, what did you run performance counters? And he did that, and he found that none of the performance counters showed any significant variance for multiple tests, with one exception, and that turned out to be L2 misses. And of course, I made it more obvious by adjusting the relative scales so that they nicely match up. But you can see with the right scale, the number of L2 misses really matches the variance of the execution time, which means, okay, clearly it's the L2 that's really at fault here. And we can actually read out the cost of an L2 miss on that platform from this graph. And turns out it's 123 nanoseconds for an L2 miss. And if we subtract this, then we get what we expected in the first place, a pretty flat curve. So now we have very, very strong evidence that it's the L2 cache misses that matter here. How can that happen? We have the same program executed back-to-back multiple times on Linux, and the L2 misses are so dramatically different. Run in single user mode. But good question, yes. Good suspicion.
The code isn't cache friendly.
Hey?
The code isn't cache friendly.
Because?
I don't know why the code just isn't.
So basically, there's something happening with the cache, right? The same program has different, vastly different, and this is how many orders of magnitude? Between basically zero. There's at least one value that's actually essentially zero compared to millions of events over 200 seconds. So basically, 1 million L2 misses per second. That's a high miss rate in your L2. It's the same L2. The L2 didn't change. The program didn't change. The data didn't change. What the hell changed?
It's something to do with the replacement policy.
Yeah?
So there could be some randomness in there, and you just get a bad.
Yep. If you think about it, what kind of misses are those? Remember the 4 C's? What are they? Capacity, No, compulsory is the first one, yeah? Capacity, conflict, and coherence. Is it compulsory misses? Obviously not, because they're the same. Is it capacity misses? The cache didn't change. Capacity didn't change. Can't be capacity misses. Is it conflict misses? It's not coherence misses because we run single CDU. It's got to be conflict misses, right? How can the conflict misses change dramatically from one run to the other? Not quite. But it's got to do with cache, with address space layout. So ASLR is a Linux defense against typical patch and pray approach, against attacks that randomizes the virtual address space layout. This is randomizing the physical layout because the L2 is physically indexed, right? And that's actually what Linux does, presumably, and actually was a new feature at the time, presumably to balance cache performance in average, right? In this case, that really hurt. And that's why it was so differently, because the next time we run, we get a different layout. Turns out it's triggered by time since boot or something. So by rebooting the system in between each execution, we got deterministic values again, which confirms the hypothesis, right? So takeaway again is check your standard deviations. Check that your system conforms to your Mendel model. If not, something is wrong. And the student did the right thing here. So, some more evaluation rules. One parameter at a time. Record and date all configurations. Amazing how many people don't do that. This is really important, right? If you benchmark, record exactly what's the configuration, when did you run it, in particular what kernel version, etc., and who did it, so we know who is responsible and who we can ask questions for. Should go without saying, measure directly as possible. Yeah, can't always do that. Pathological data. This before was sort of a particular case of pathological data, right? Every now and then, the kernel would allocate physical frames in a way that maximized cache conflicts. Powers of 2, we're used to think powers of 2 are good, and in most cases they are. Sometimes they're particularly bad because they can, in particular, lead to particular high cache conflicts because they sort of tend to have cache lines falling on each other. In which case you may just be better off using one of a power of 2, etc. It really depends a lot on the circumstance. This is just some of the things you need to consider. Because what's pathological depends very much on the circumstances. And just in case I haven't mentioned it before, have your Mendel model ready and actually use it. And always make sure that what you see conforms to the Mendel model, and if not, dig deeper. And yeah, so can't say that often enough. Another simple case, memory copy. So this is just, what's the cost of copying a buffer of data to another buffer? Execution time as a function of buffer size. What do you expect? What's your Mendel model?
It's linear to the buffer. Linear to the buffer size.
The starting point clearly is you expect the execution time to be linear in the buffer size. And if you do that, then you can say, well, it's not quite. And the effect is much clearer if we look at what's basically the derivative of this curve, which is the throughput, as a function of buffer size. Then we get a really, this is a typical case, derivatives rough up the data and get some things, make them much more obvious. We really have a number of interesting zones. So the derivative, according to the simple Mendel model, because you said you expect a linear relationship, that means the derivative should be a constant, so you expect the flat curve for the throughput. It's all but flat. What can you see here? You can see, actually, read a lot about the processor from this curve.
Perhaps there's a switching of modes. We'll see it's linear actually in one section at the beginning. Non-linear.
There's linear sections with non-linear transitions, yes. what happens at those transitions? I heard the right word somewhere. It's a cache, yes.
Yeah.
So basically, this transition here, the first slope down is the L1 cache. So before that, data fits in the L1 cache, and then you overflow the cache, and you get a significant performance degradation. We expect that, right? It wasn't part of our simple mental model, so we have to update our model. It's normal, because basically what this means is our measurements is more sensitive to details of the model than what we started with. That's totally valid. Always start with the simplest model first. Never start with something overly complex. Okay, and what's the second downward slope? L2 cache, yes. You can actually read the cache size out of this, basically. So this has a 1 megabyte L2 cache, and the slope bottoms out at 0.5 megabyte. And what's the thing at the beginning where it goes up? Nope. It's much more trivial.
Can we have registers?
Hey?
You can just put things in registers, right?
Yes, that could be part of it. You sort of have a register set, which is basically a cache, yep. But even more trivial, loop overhead. That's most likely the culprit here, right? That's why you try to avoid small iteration counts, because loop overhead really is significant there. So again, mental model, make sure your observations conform to it, otherwise understand why not and update your mental model. So getting to a loop overhead, you try to eliminate that, and the safe way, which is not guaranteed foolproof, is just run the thing without the test and with. So if you're benchmarking system calls in SEO4, for example, replace the syscall instruction by a no-op and measure both versions and subtract the no-op one from the other one, and that gives you then the real syscall cost, and that should exclude all the user level overhead. You have to be a bit careful. If you have an aggressively optimizing compiler, it will certainly throw away the first loop. But there's no reason to optimize that bit. Well, maybe there is, because there's a benefit of having all your benchmarking data in registers, which you only get when you turn compiler optimization up to at least a certain level. But you don't want to do them too high, otherwise the thing will throw away the whole loop. Using volatiles is generally a good idea to stop the compiler from throwing stuff away, because it can't make assumptions that they behave like normal memory, etc. Yes?
Is most profiling done with compiler optimizations at all? Like, is there any reason to do with zero optimizations?
Well, normally you try to profile the code that you're actually using, right? Because if you profile unoptimized code, then it's not going to behave like the optimized code. But sometimes you can't do that, right? In particular, obviously, mapping the results to actual code becomes harder, etc. So compiler optimizations are always a tricky thing in terms of benchmarking. You really have to understand what possible effects could happen. And often if there's something weird happening, like things taking no time, then always suspect the compiler is throwing stuff away. So this is an important one. And then we have relative versus absolute data, and this is actually one of the things that started my list of benchmarking crimes. This is an actually published paper, CCN 09, IEEE Computer Communication and Networking Conference or something. It's a second-tier conference. And this was a time when I was working for my company, Open Kernel Labs, and we did shipped SEO4 no, not SEO4, the predecessor L4, among others, for doing virtualization of mobile phones. And this was a competitor, and they published this paper showing how much faster they were than us. And I knew that was wrong, because I knew from client evaluations that we were faster than them. So but the thing is, this is all the data they had in the paper, and it's hard to read because I could only grab a bitmap from the paper. What you have is different benchmarks, so that the lines going out are the different benchmarks. This is a so-called radar plot. And the blue line is normalized to their system, and the green line is our L4 system running Linux, and they claim, okay, it's much slower. Well, in this case, yes, it is much slower. They didn't say what they're doing. They just say, okay, between 2 and 20 factor overhead, without defining exactly. And no native Linux data. So really, if you do benchmark a virtualized system, then of course the real baseline is the native system. Had they provided a native system, I could immediately have told that this is wrong, this is not what we see. It actually, I knew anyway was wrong because I knew our overhead over native Linux, and of course, put in the open source, so if you could just get it out of the box and build it, had all benchmarking and profiling turned on. Of course, profiling slows down the kernel, right, and by a significant factor. So what they did is really cheated. They had compared their well-optimized system with ours with profiling enabled and debugging enabled and all that. And of course, that's really cheating. So this is definitely a benchmarking crime. And the thing is why it's sort of, you can't actually prove what's happening because they didn't really provide the proper baseline data. They had only relative to their system with unknown configurations. This is another one I came across in real life. This is a database paper. They measure database transaction throughput over the number of concurrent processors, and they get this curve. Okay, scales reasonably well, right? What information would you like to know to say whether this scales reasonably well?
What kind of load is it? Like read
It's a standard benchmark, standard transaction benchmark. They declared that. What's the important information missing here? The number of cores, yes. Now, if I tell you that the number of cores is 32, then, well, okay. Of course, if you have more CPUs than transactions, it's trivial to scale, right? But we already see it flattening out. And of course, this is not the right way to run your database. You want to have the database system always to have work, so you generally have at least somewhat more transactions as you have cores to make sure you keep them all busy. So this is not a good thing. And then if we complete that, and this is the word we actually, you see a typical performance collapse when you get overload. So their scalability is actually awful. The system scales as long as you have idle CPUs. Big bloody deal, right? Okay. This is definitely a form of cheating, and it's a form of a selective data set. They basically only showed the good bit, and not really how awful it really gets if you get into a more reasonable domain of usage. So that gets us to sort of comparing with competitors, which is inevitably what you do if you want to write a research paper. You have to compare yourself to the state of the art, and that implies benchmarking, typically benchmarking against other systems, etc. And there's where if you can compare to published numbers and they're on the same hardware, which is extremely rare, then you can just run your stuff and compare and quote the published numbers. In most cases, you don't have the same hardware. You have to run their system against yours to compare. And then you really get into the domain of having to be fair against the competitor, which is what the other guys in the CCNC paper very clearly did not do. They did an extremely unfair comparison. And there's other ways of cheating with benchmarks. This is a classic compiler. People know about that one from way back. Back in the 80s or so, first I saw that on a Prolog system. People started building into that compiler optimization specific for the standard benchmark suite. So the compiler would actually notice that it's running the standard benchmark suite and then have specific optimizations that really designed for the benchmark suite. Hey?
Is it a bit like Volkswagen?
Yeah, quite so. And then Samsung pioneered this on operating systems about 8 years ago.
They cheated on Geekbench, I think.
Hey?
They cheated on Geekbench. It's like an app that got a lot of commercial.
So what Samsung did is they had a special undocumented hardware mode where they basically overclocked the system, and that was only turned on when running this benchmark suite. A really, really extreme case of cheating. The good thing is they got found out and they got really got highlighted, and they stopped doing it after a while. But that's pretty bad. Benchmarking a simulated system. Now, sometimes you have to use simulations, but a simulation, of course, is always an approximation of a real system, right? That's the whole point of a simulation. And you have to be extremely careful with your assumptions there. And I've seen cases where that wasn't the case. And I've seen, this is when we did some work on multiprocessor, scalability of our hypervisor on Itanium. And there was this company selling this thing, and they showed the scalability, I'm not kidding you, by just running multiple copies of spec on different CPUs. And of course, the fact that it didn't scale perfectly meant they actually had some serious overheads. We didn't even think of running this benchmark because it was obviously meaningless, but we should have, because we would have scaled perfectly. They did not. And honestly, I saw that in real world, where people do networking performance, do something to the networking system, and then run performance measurement. If you look at the benchmarks they run, they're all CPU bound. And then they claim, okay, the performance is unchanged. So I'm not kidding. I've seen all these lies in real world. It's amazing. So lying in public didn't start with Trump. And then, as usual, I run out of time here. I just got one thing to come, which is also real-world stuff, which is what we, again, example from the company a few years ago. The question is, what really establishes good performance? And that's not often not easy, not trivial to see. For example, here, virtualization overhead. So, as I said, we did this hypervisor, and at that time, the most common mobile phone operating system was a thing called Symbian. Doesn't exist. It came out of Nokia, basically ran Symbian, and a few others as well. And so we have this comparison: native Symbian versus virtualized, and it runs about a factor of 3 faster on a null system call. Question: is this a good result or a bad result? Factor of 3 seems a lot, but, and yeah, this is an ARM processor. The main important thing is here that, okay, we have native 93 cycles, 200 cycles overhead. K-Schmiss is about 20 cycles. The reason that I flagged this is it's probably to do with that. And factor 3 from virtualization, well, if you think what happens, the system definitely needs to do much more in the virtualized system, because the native is the null system call is trap in the kernel, come out, so it's just 2 mode switches. Whereas if you virtualize this, then you do basically context switch into the hypervisor and back, so you have 4 mode switches and 2 context switches and 2 more times saving and restoring state. So you expect that to be significantly more expensive. So the null system call is obviously the extreme test for a virtualized system. And if we want to understand whether this is really good or not, then we go back and use the PMU. So we look at what are the different metrics the PMU gives us, and we see that most of the things are harmless. We have many more instructions. Well, that's not surprising. It's amazing that Symbian needs 30 instructions to do a null system call. That's a lot of code to execute for a null system call. The virtualized system does 2 real system calls and an approximation of a null system call, and it only takes 95 extra instructions. It does 200 cycles, so the ratio of instructions to cycles is fairly bad here. It's more than 2 cycles per instruction, and that's because we have a significant increase in cache misses. And turns out this was okay because of basically something we did for optimizing performance overall, not this null system call, required basically losing the cache in this case, and that's why we get this number of cache misses. So the takeaway is, yes, after I saw that number, I know, yeah, performance is good. We don't have a problem here. Another one, same system. This is the Symbian benchmark suite. It's a bit similar to LM-Bench, but not quite the same. And it gives you different metrics, and we see that context switches, the context switch rate. So this is basically just doing context switch in a type loop. We do about a third less. So that's some overhead. Create and close files. We have higher latencies there. Suspend operation has higher latencies. Looking at these numbers, you can't really tell whether this is good or bad. And the first step to find out is get a better representation. The way these things are represented are useless for analysis. So convert the same data to something that's more meaningful, express everything in latencies. So we look at microseconds throughout, and we see, okay, difference between the virtualized and the unvirtualized system is 0.62 in the context switch. Remember, our null system call virtualization overhead was about half a microsecond. That's close enough. So basically, this means probably we're there as good as we can be. It's a bit higher for create and close. And in order to find out what that means is we convert the overheads into cycles. And then we see 230 cycles for the context switch. Remember, before it was 199 just for the null system call. So this is a fairly good result. The other case, it's significantly higher. Turns out this actually does 4 system calls, all have to be virtualized, etc. And then we know, okay, this is actually a good result again, and suspend, we're back to the overheads of the null system call. So basically, by converting this useless representation in something that is actually more meaningful and lets us compare to things we already know, we find out much more information and find out that, in particular, this is actually good performance, so we don't have a problem. And final one. So this is running floating point benchmarks, basically simple floating point iterations. A big loop that does floating point operations on a big buffer. And we have native and virtualized. So this is no kernel entries here. This is pure user level. Why do we have any overhead from virtualization in the first place?
Page faults. Page faults.
Interrupts, yes. The timer interrupt. That's the only thing which invokes the hypervisor, is the timer interrupt. So does that account for this overhead? Let's convert to per tick, because it's the normal 1 millisecond timer tick that's actually visible here. And we see, okay, we have 2.8 microseconds overhead per virtualized timer tick. Remember, the null system call was about 3/4 of a microsecond, so we are a factor of 3 away. Null system call we benchmark with cold caches, with hot caches. This is cold caches because we have a big user level buffer that overflows the cache. So when the timer tick happens, the hypervisor gets invoked with a cold cache. you expect performance to be, the overhead to be higher. Remember, we had about 20 cycles per K-Schmiss, and we don't need all that many K-Schmisses to account for that. So basically, yes, looking at the full picture, this sort of overhead makes sense because of the way the architecture operates. And then I know, yep, we can't really do better on that one. So again, this is understanding the problem and where the cost comes in, and using the right representation helps a lot. So to wrap up, really look at your variance always. Have your model, your mental model of the system behavior, and check the actual behavior against this model, and use the tools to analyze, in particular the PMU. And there is my annotated list of benchmarking crimes if you're interested. All right. Sorry for running 5 minutes over. Any final questions? Cool. See you Thursday.